Right, this is questions on nuclear physics. Over here we have a mass balance. Notice that the 4 nucleons separated, 2 neutrons and 2 protons, have more mass than a helium nucleus when they are combined and bound together. This of course means that when we fuse these 3 nucleons together, mass must be released, and it's released in the form of energy. That energy is very, very small for one nuclei, but if you have billions of them, or trillions, the energy release can be extremely large, and this is what, of course, is released during a hydrogen bomb explosion. Okay, question 1. About activity. Given an isotope of phosphorus, phosphorus 32, and we're told that the activity at time 0 is 10,000 becquerel, and the half-life of this particular isotope, phosphorus 32, is 14.3 days. We're asked to calculate the activity 45 days later. So the equation to use for this is the activity equation, where activity at any time equals the initial activity at time 0 times e to the power of minus lambda t, where lambda is the decay constant, also the same or equivalent to the probability of decay per unit time when the time is very, very short. So we can write another expression for that, lambda, the decay constant, which is the natural log of 2 over the half-life of the isotope. So we have the half-life in days, but conveniently we don't need to change it to seconds because, of course, we have also been given the task of calculating the activity 45 days later. So we can keep, in fact those days will just simply cancel out in the equation, as you can see. So if you plug the numbers in, the activity A will equal 10,000, the initial activity, times e to the power of, it's going to be a rather large bracket, log 2 times 45 days over the 14.3 days. So that those days cancel out. And you then will find the answer to be, hopefully, 1130 becquerel, and that's the 3 significant figures. Question 2. Americium-241 has a half-life of 433 years. Question A, what is the decay constant? So for this we are going to find this value in seconds, so we need to change the 433 years into seconds. So the decay constant lambda is log 2 over the half-life in seconds. So we need to multiply that by the number of seconds in 1 year, which is approximately 3.16 to the power of 7, just taking 3,600 seconds in an hour, timesing it by 24 for 1 day, and timesing it by 365.25 to take care of the leap years every 4 years. So that should give you 5.1 times 10 to the power of negative 11 per second for the decay constant. Okay, for part B, to find the total activity of 1 gram of americium-241, in 1 gram we need to realise or work out the number of nuclei there, and that can be found by using 1 gram over 241 grams, which is the mass number, and multiplying it by Avogadro's constant, 6.23 times 10 to the power of 23. So that'll be the number of atoms, and of course the number of nuclei must be the same as the number of atoms. So that gives us a rather large number. Actually, I'll just work out the activity straight away using that. So we've found n, essentially, big N, and we've got lambda worked out before, so it's 5.1 times 10 to the negative 11, times 1 over 241, times Avogadro's constant. So, punching that into the calculator, you should get 1.3 times 10 to the power of 11 becquerel. Again, the two significant figures. Part C of this question, how much of this remains after 1,000 years? So the fraction remaining after any particular time t is n over n naught, and that of course is equal to e to the power of lambda t, and we have lambda, and now we just need to make sure we convert 1,000 years into seconds again. So we'll get the following: 5.1 times 10 to the power of negative 11 is lambda, times the 1,000 years, times the number to convert to seconds, which was what, 3.16 times 10 to the 7. So punching that into the calculator gives us 0.20. So that's the fraction remaining. I suppose you could say that's 1/5 as a pure fraction. Okay, question 3. Given the average binding energy per nucleon of the nucleus 56, iron 56, is 8.7 mega electron volts, we're asked to calculate the binding energy of the nucleus, the entire nucleus, in joules. So the thing to realize is that the binding energy of the nucleus is simply equal to the binding energy per nucleon multiplied by the number of nucleons in that particular nucleus. In this case it's 56. So simply 56 multiplied by the 8.7 mega electron volts. That gives us 487.2 mega electron volts. Now that's to be converted into joules. And of course to do that we simply multiply by the charge on one electron. So binding energy equals the 487.2 times 10 to the power of 6 for the mega, times 1.6 times 10 to the power of negative 19 coulombs, which gives us 7.8, the two figures, times 10 to the minus 11 joules.